First of all, thank you all for coming. This is the first time we're doing this type of seminar, qmeets. Maybe just a few words about the seminar series itself. So we will have every month one talk, always by two people, 20 plus 10 minutes each, with the idea of either having a duo of a theoretician and an experimentalist, which work together on something, or a young person and a PI. The idea is that sometimes when you have really, really nice and good results, it still takes some time to deliver them in a way such that people from different fields can appreciate them. And therefore, we think it's nice to have somebody who gives like a more broad introduction into a field, possibly somebody who is really well known for these types of works, and then somebody else who is talking about the recent breakthroughs. Nowadays, we are extremely lucky because we have two people which fulfill both categories, namely a PI and a postdoc, and additionally, somebody who I believe is a theoretician and an experimentalist at the same time. And Patrik, I believe you consider yourself as an experimentalist mostly. To give some introduction and background of our two first speakers, Silke is, in my opinion, one of the pioneers of analog gravity with fluid systems. Already in her PhD, she did some very influential work on how to simulate FLRW universes in cold atoms. And also in her two postdocs with Bill Unruh and Stefano Liberati, she focused a lot on quantum simulation of some cosmologies. I remember well when I was visiting Nottingham, she told me the story about starting to doing experiments herself by putting rocks into a toilet and then studying the fluid flow, which is an amazing story. When she went to Nottingham to build her own group, she bought an extremely large water tank. Maybe she's talking about this today, I don't know. If not, you can watch a Netflix documentary where this is also appearing, called Black Holes, The Edge of All We Know. And recently, Patrik and she started to build a superfluid helium setup, which is also what probably Patrik will talk about. About Patrik, he did his PhD in Prague. As I said, was the main person responsible for building the superfluid helium setup from scratch. And is also doing a lot of things outside of classical research, namely playing with Lego to demonstrate quantum optics, or in general, investing a lot into education. So in case you speak Polish, you may actually buy one of his books, which contain a lot of nice physical problems. All right, this is all about the two speakers, and now the stage is yours.
Okay, thank you, Toby. Thank you for organizing this. I think this is quite a nice thing to do, to give a talk with Patrik together. Now, as you said, so I will talk a bit more about the general field of research and sort of then lead up to what Patrik needs to talk about, sort of our newest results. Okay, so I want to quickly just say that we, Patrik and I, are part of what's called the Quantum Simulators for Fundamental Physics community, consortia, that is 27 funded people in the UK and external partners and collaborators. If we add it all up, this is almost 80 people, and we are working all towards this, or all in this field of quantum simulators for fundamental physics. And in particular, over the last 3 years in the UK, we have been setting up 4 different experiments. And one of this is the one Patrik will be talking about. And also this consortia gave the opportunity for Patrik, Patrik is hired as part of this funded project. And just as in what you said at the beginning, when you have experiment and theory, this was really at the heart of what this application was about, the intersection between theory and experiment. So I thought it's quite nice that we get the opportunity to talk here. Okay, so what I'm going to talk about is the possibility to to simulate, and I have to then tell you through by which means to simulate classical and quantum field dynamics in a controlled laboratory environment. And so the first question one has to ask, why would I care, or what are the interesting problems within classical, or mostly perhaps quantum field theory, field theoretical problems that we would like to investigate? So quantum field theory is a really wide field, of course, right? It's a modern pillar of physics, but there, to sort of get a bit of a structure in there, one could say perhaps we are looking at interesting effects in two different angles. The one, we say we have interacting fields, how fields scatter and turn in each other. That is one route forward. And there, one can consider far from equilibrium processes, scattering processes, but also one could add phase transitions within quantum field theory, so problems that are highly non-equilibrium problems. So these are sort of hard and interesting problems. However, if you have non-interacting fields, that doesn't mean nothing is happening, because these fields can couple to something else. They can couple to gravity, and they do this through coupling to a curved space-time. And then also, if you look at fields in general, you can also couple through some detectors to this, so you can interact with them, and this becomes the measurement process. And what we are interested in particular is quantum field theory, and as you probably can see here, quantum field theory are relativistic quantum field theories. Okay, so because this is a very broad audience, I just want to give an extremely ad hoc or simplified way of how we do field theory on a curved spacetime. So writing down an equation that we all know, this is a second order partial differential equation. It's the wave equation that we all know, appears in many fields in physics, seismic waves, acoustic waves, light waves, name it. It is something that reoccurs in so many areas in physics. Now, if you look at this wave equation here, you have this c here. And the c, if it's light, it would be the speed of light. If it's acoustic waves, it would be the speed of sound, for example. Now, the same question that you may in a simplified way could ask, if I have a field propagating on, is there another way how I could write this? And if you particularly look at, for example, light propagation, and look at that wave equation, there is another way to write it, which is simply by introducing the geometry of flat space-time, which is the Minkowski space-time geometry. And what you've done here, you just rewrote this wave equation in this, perhaps by looking at it a bit more compact way, but also a bit more mysterious way, because here you still have to define this eta AB, which is the flat space-time geometry. These two equations are exactly the same. It's just a different way of writing that, okay? What you have gained by doing that, you can now ask yourself, well, what if the field is not propagating on a flat space-time geometry? What if I want to now look how this field propagates around a curved space-time geometry, a black hole, or in the early universe and rapidly expanding universe? So here you could say, why don't I just do an ad hoc replacement and replace this eta AB with a general curved space-time geometry, GAB. Okay, I'm sorry. So now this is the most ad hoc way to do it, the simplest way to do it, what we call also the minimal coupling. And so this is sort of ad hoc how we postulate field theory on curved spacetime, field dynamics on curved spacetime. Okay. Now, this is it's sort of like a step 0, step 1. This is the most conservative, but also the most sensible way to look at fields propagating on curved spacetimes. And you can ask yourself, okay, so this is really a far distance from, for example, really unifying gravity and quantum fields. It's not really quantum gravity, it's really modest. But what that area of research has is wonderful, interesting physics, okay? And that's why it's such an interesting field of research, in particular to me. So let me give you a few examples that you're all familiar with. If you look at quantum field dynamics around a black hole, you get a Hawking radiation. That tells you that although black holes only gobble up things, nothing can escape. If you look at the quantum field around a black hole, you will see that, in fact, there are processes happening that lead to the emission of a thermal radiation, which is dubbed as a Hawking temperature. Okay, this is very quick, but just to say, if you take a rotating black hole, you get a plethora of new effects. You also have the Hawking effect, but you can also look at classical field propagation, and you get what's called black hole superradiance. That's a process that allows to give a shine of energy, rotational energy, onto the surrounding fields, and through this process, a rotating black hole can slow down. Okay, absolutely pivotal. If we look at the early universe, the beginning of everything, we are postulating that perhaps there was a quantum state, so there was really absolutely nothing. And the question is, how do we get from this to where we are here today? And in the very early stages, quantum field dynamics on curved spacetime is the dominant theory. And then you don't need to have a fancy spacetime geometry. You can just look at flat spacetime geometry. And then if you ask a question of how many particles are there, are we in a vacuum state or not, that really depends who is asking the question. And in particular, if you are an accelerated observer, then you can presume the empty space full of particles. So this is dubbed as the Anno effect. So this is just, it's not really explaining what this is, but it just gives you a bit of an idea. There's lots of nice stuff to look at. And the only problem here is, or perhaps not a problem, more a challenge, is that these effects are extremely hard to measure or to observe or to actually set up experiments, as in the Anno effect, because they're really, really small. And so there is no way at the moment, or most of these things, that we actually see that. And so we are lacking something which is really crucial. We're lacking experimental or observational feedback on our theoretical models. And that means that the understanding is not complete and that the theoretical models are all very idealized. So in the absence of anything better, in 1980, Bill Unruh, the story he tells, gave a lecture in fluid dynamics, and he came up with an idea. He started thinking about what happens actually. What happens if I put a little speaker into a waterfall, and let's say, or a river flow, and you put a little sound speaker in there, and you look at sound propagation. And if you're in a regime where the fluid flow is slower than the sound waves in the system, these sound waves can propagate in all directions. But of course, if you look carefully here, if the flow is increasing downstream here, they propagate faster with the flow rather than against. And so once you have understood that, you say, what happens actually if your river flow would exceed, if there's a point where you introduce a surface in your river flow where the sound speed, the normal of the sound velocity on that surface is equal of the fluid flow velocity on that surface is equal to the sound speed, what is happening? And what is happening is, in fact, if you have your little speaker right here on that surface, all the sound wave would get dragged downstream, nothing can escape. And that reminded Unruh on the idea of, this is similar to what happened around black holes, where if you look at fields on the horizon, everything would be absorbed from the black hole. And this sort of led him to go back to his office and do a calculation by linearizing sound, looking at sound dynamics in fluids, here liquids. And what he notices, actually, by rewriting my fluids equation, by linearizing the Navier-Stokes equation, putting a lot of assumption on it, such as an ideal fluid, and I get a set of equations, but I can rewrite them in this compact way, where now this GAB really is an effective metric that is provided by the fluid flow. And so if you look at this now, there are a few things that we need to understand. The first thing is V here is the background flow. C squared is the propagation speed. In this case, which I just explained, it is sound waves, but I will talk more about this. And then you have this metric here, and when I have this 1 here in the sub-index here, is d times d. It means this is depending on the spatial dimension of your system. If you have a bulk fluid flow, then this will be a 3 plus 1 dimensional effective metric. If you work with a 2-dimensional system, as we will discuss later, the effective metric would be a 2 plus 1 dimensional. And if you have a highly confined system and you have a 1-dimensional system, you would get a 1 plus 1 spatial in terms of the dimension of the physical system. You get a 1 plus 1 dimensional system, effective metric. Okay, so I have not really fully explained this, but you need to trust at this point that sound dynamics can be cast in this equation. Okay, so, but we need to discuss a bit more what this psi here is, because I haven't really explained that. And what that psi here is, that is usually when we talk about, in fluids, we talk about density and density perturbations, but we also talk about perturbation in the background flow. Now, if it's a Navier-Stokes equation, or if it's a fluid flow that has that is not irrotational, then you would need 3 parameters to describe that fluid flow. But we are reducing ourselves to irrotational flows. So that's one very important thing, and that will be picked up in Patrik's talk later on. If it's an irrotational fluid flow, you can write the velocity field in 3 dimensions as a gradient of a scalar field. And the perturbation of this scalar field, right, this is where you get the analogy from. So these are small fluctuations in the velocity potential. And this is where we have this analogy. And then, so this was the first realization. Now I have to say, when Andrew wrote down this, when he discovered this analogy, this mapping to field theory in curved spacetime, he was already assuming that this more or less was an ideal fluid. And in fact, the simplifications done fit much better to a superfluid. And in fact, if you then look at superfluids, such as, for example, starting with the Cross-Pitaevsky equation, which you can, by using a Madelung representation, by switching to phase and densities, you can write down, you can derive fluids equation. If you linearize those, you base these fluids equations are ideal fluids, and clearly for these ideal fluids, you get the same thing. Now, what have you gained? Now here, you can really say, instead of having classical fields like this sound dynamics, which sound dynamics, as the conjugate momentum to this would be the perturbation in the velocity field. In the superfluid, your sounds and your perturbations in the velocity field, they're quantized. And so in this sense, you now have a quantum field theory on an effective curved spacetime geometry. And now, of course, that was not all, and this is also extremely important for us. When you talk about fluids, usually we have, like, we look at a bulk of fluid or liquid, any fluid, a gas or a liquid. And in particular, when you work with liquids, then you can also have interfaces. And these are really 2 coupled Navier-Stokes equation, air, water, for example. And that interface that forms between them, this is a completely different, has a completely different dynamics, its own dynamics, and these are interface waves. And these interface waves, again, obey a wave equation, but they have different sound speeds, for example, propagation speeds. Okay, and then of course, when we talk about quantum liquids, the most, the historical quantum liquid was not Bose-Einstein condensates or BSEs. These were really quantum liquids, and this in particular helium, helium-4, and helium-3. And so all of these systems, right, you can find this analogy. And that makes it really interesting. So what we are working on is quantum liquids, and I want to say quickly why quantum liquids. So quantum liquids are fantastic because when you start to cool them down, at the beginning, so what you do at the transition temperature, you gradually reduce the normal component. So it means you can think of them as two component systems where you have a superfluid and a normal component. And as you decrease the temperature in your quantum liquid, the normal component decreases. And this means as you turn down the temperature, it becomes more and more quantum. But as it goes through, it actually has distinctive regimes, and which means you can tune the temperature and with it dissipation in the system. And another really fantastic thing about these quantum liquids is because they're liquids, they form free surfaces and films. And depending how the film thickness is, you have thin film helium or you have a bulk of helium, you have sound waves in between in the bulk, but on the interface, you have this interface dynamics we're interested in. And then the really, for me, one of the most exciting things, and that's what Patrik is going to use again, is that they exist in both micro and macroscopic regimes, so over large length scales. So if you have the money and the patience and the resources, you could set up a cubic meter of superfluid helium. And it can last for 50 hours non-go. So without it can keep it down and cool for almost indefinite if you were to put your effort into it. So these are really great features, and Patrik will need that fact that we can have large systems. And then the key challenge is the control of the superfluid flow and film thickness, the detection of the interface wave dynamics, because that's what we're interested in, that's what we are setting it up for. And that, of course, you have this translation key because we want to map it to quantum field theory and curved spacetime. How do I do time-wise?
I think maybe 5 minutes.
Okay. So then I will be quick and just focus on what I really need to introduce Patrik's talk. So again, when we look at this space-time geometry, here I wrote it down for a 3+3 dimensional system, okay, without any confinement. So what can you get? So in general, I write this down. Here I have the sound speed and I have the background flow. They're all flat. They all have this thing that on the spatial slice here, they're diagonal. And so what you can set up what kind of space-time geometries. So if I want a flat space-time geometry, I need to work with a homogeneous, so that the sound speed, for example, is everywhere the same, and a static fluid. Okay, so homogeneous and static. If you want to set up a black hole horizon, you need to set up stationary flows. Okay, if you want to set up a cosmological space-time, you need to somehow get time dependence in there. There are various ways. One is to assume that all the velocities are zero, but that my sound speed change over time. And you can do this by changing parameters the sound speed depends on. For example, the density, or in our height, the film thickness height. If you were to change that, that would change over time. That would introduce a time-dependent space-time geometry. So I will only glance through this. So one of the things is you can look at flat space-time, and here, as you can see, the c squared is here what goes in this g naught component in my metric. And what you can do here, this has a different signature than the ones here. So meaning different sign, and you can flip the sign as well, and you can go from Euclidean to Lorentzian signatures, just if you're interested in this. But in general, you can ask yourself, what is the effective Lagrangian? And in particular here, focusing on interface wave, and this is a more complicated thing, which means that the waves are actually can also interact with each other. And that makes it really interesting. It's something that the field is really generally moving into it, looking at interacting fields. It's also the experiment that we at the moment also writing up. So you have to think about this. There's a part that couples to an effective geometry. You can also create masses by playing with symmetries and adding more fluids. You can stick in little probes that can act as anode detectors. And then you get a wonderful, nice interacting waves that scatter. And in fact, these additional terms is precisely what cosmologists, for example, are interested in. So this is a really interesting thing. There is not one experiment that could do all of it. And you need to set up experiments that do exactly what you're interested in. For example, if you want to probe the anode effect, you need to bring your anode detector with you. Okay, what Patrik is going to talk about is analog rotating black holes. And he's going to talk about analog rotating black holes that have in a liquid, that have an interface, and we look at the interface dynamics around a vortex flow. So we need a stationary fluid flow. And what we need is a radial component. So it's a draining and needs to get recirculated, and an angular velocity component. So it's a two-dimensional velocity field. Okay. And the reason why rotating black holes are so cool is because they have, just as, you know, non-rotational black holes, they have what we call this event or apparent horizon, this region from where no ripples, no excitations can escape. And this is when the ripple speed in the systems is equal to the radial component. That's where you get this effective horizon. But already, if you look at the total velocity component, when that is equal or larger to the ripple speed, your interface waves, then you get this ergosphere. And this ergosphere has really cool things. Once a small perturbation enters, it cannot counter-rotate anymore. It has to co-rotate. We call this frame dragging. And all of these wonderful, you know, effects caused by coupling to this effective metric, they cause wonderfully nice physics. Okay. Great. I need to come to an end, but I just want to motivate Patrik's talk also from another point of view. So when we started setting this up many, many years ago at in Nottingham, I formed this black hole laboratory where we tried to set up a gigantic or a big hydrodynamic rotating black hole. Now this, as you can see here, this is a stationary draining flow, and Patrik will talk much more about it, and I have one more slide. And then what we are interested in, we look at how the wave propagation, how the wave interact with this vortex flow. This is super classical, okay? It's a 2 + 1 dimensional effective metric caused by that vortex flow. Okay, so I think I'm running late. This would have been a video, but what you could see here, I cannot run it unless I go out, but running late, I just explain quickly. We have a plane wave that interacts with this vortex flow. And what we're expecting, because if these waves probe an effective curved space-time geometry, we know if we get close to a black hole, our geodesics are strange, doing weird things, which means that they are part of the wave that has to be absorbed by the effective black hole or vortex flow, and other parts that sort of get messed around and dragged along. And this creates this wonderful interference pattern between the waves passing from the right and from the left, from co- and counter-rotating parts of that coherent wave that we sent in. Oh, it is working. Okay. Okay, so how do we know, and this is what Patrik also needs to do, and very quick, how do we know that this really can be mapped to curved space-time geometry? And what we did a series of experiments, and we probed that wave dynamics. So in one sense, we worked with this coherent wave, different frequencies, and what we wanted to see if superradiance occurs, if there's energy transferred from the vortex flow, from the background flow to the little waves. And so that was one of the first things, and that was really encouraging. We did see that there was this transfer happening. So one of the effects that we expect, such as superradiance, did occur. Another thing that we realized, if you don't do anything to this vortex flow, it kept on sending off this counter-rotational signal noise. We analyzed this and we realized this can actually be mapped to something in the black hole physics that's called a black hole ring down. Patrik will talk about this. Now, so we started here already, instead of sending a signal and see how it propagates, we went to something that was already a noise in the system. So somehow really like exploring different regimes. And of course, if you have a quantum system, you want to see how quantum noise gets affected. So this is sort of the holy grail in analog gravity, is that you have such an accuracy and control that you can really focus on quantum noise dynamics in these systems. However, this is the right way to start, make your problem easier if there's more noise to study. So one thing is to go to quantum is, of course, to go and exchange your classical liquid with a quantum liquid. And it's not only because you want quantum wave dynamics, because really you want to go to this ideal fluid approximation, and you want to have dissipation, damping, and other effects in there. So going towards the quantum regime is not only to study quantum field dynamics, but to have better simulators. And the only problem, and this is what Patrik will talk about it, if you have a superfluid, for example, a two-dimensional superfluid, I do this now. This here. And if you start rotating it, what you get is, because it is a superfluid, you get quantized rotation. And that means, Patrik will talk more about this, these quantum vortices, as they're called, they have one problem. When you want to speed up a superfluid to very rapid speeds, these quantum vortices, they take on discrete values of quanta. And this, it's favorable for them to decay into many discrete singly winded quantum vortices. And they have this property that they want to spread out. And this is the problem, because we want to keep all this vorticity and all the vortices together in the center so that we are surrounded by an irrotational fluid flow. And the question is, how can a system accommodate a structure like this? How can you set up giant quantum vortex flows? That's Patrik's talk. And with this, I'm passing on to Patrik.
Thank you, Silke, very much. I'm just wondering, isn't there supposed to be a discussion now, or at least a short Q&A, Toby?
Yes. So maybe let's first thank Silke for this amazing talk and introduction. And since the whole idea is that the audience can be broad and the first talk should be introductory, everybody can now ask any question. Please don't be shy. If you're from a different field and ask something very basic, doesn't matter, just go for it. So please raise your hand in Zoom, and then we will call you and you can unmute and ask something.
You can also ask in the end if a question comes up for me at the end. I'm happy to take it.
Yeah, sure. Okay, I don't see any hands raised now. Then I would say we just proceed with you, Patrik.
Perfect. Thank you. Just return to the pointer. Amazing. So yeah, thank you very much. This is a very unusual setting, but it's quite cool that the hard part of any talk I'm giving is now done by Silke. So I thank her very much for providing a very nice introduction. And now I'm going to pick up on what Silke said about simulating black holes in the lab. And I'm going to discuss a very concrete example. So I'm going to discuss actually the experiment that is photographed here by our PhD student Leonardo. So it is a superfluid simulator of rotating curved spacetimes. So yeah, this image has already been shown in Silke's introduction, and this is actually a picture from the giant experiment that we have here in Nottingham. And I joined the group 3.5 years ago, and this experiment was already up and running. And the first time I entered the lab, I was shown this experiment. It was absolutely amazing. It is a massive volume of water. I think it's around 1,000 liters of dyed water that is spiraling through a central drain, which is in here. And the green light is not a coincidence. It is actually green dye that is dissolved in water in order to increase the reflectivity of the interface of the surface of water. Because above this system, Silke actually developed different techniques how you can accurately read out in real time with spatial resolution the interface height in order to then transfer it into surface waves. And well, my background is in low temperature physics. So yeah, I was basically told, okay, so we need this experiment, but in superfluid helium. And I was very worried. How can we make this into a quantum regime? Because superfluid helium is indeed a quantum liquid, so it creates an interface, and there are only two isotopes of superfluid helium that have interface. All the other quantum fluids are gases, or systems that are too dissipative to form a well-defined interface. But superfluid helium is also very cold, and it is usually not poured into open tanks which are terminated with drains and so on and so forth. They are usually kept in very non-transparent containers such as this this one massive container that is in at CERN. And the reason is that, you know, all these containers for superfluids, they need to be extremely well thermally insulated, because superfluid helium occurs only at very, very low temperatures, less than 2.2 Kelvin. So any room temperature heat flux would evaporate everything that we have in the experiment, and we couldn't carry on. But if we manage to cool liquid helium below 2.2 Kelvin, then it behaves according to quantum mechanics. And well, in simple terms, and Silke already opened this up, we can actually write the macroscopic order parameter in terms of density and the macroscopic phase. And this macroscopic phase actually accounts for the velocity potential. So its gradient actually gives us the superfluid velocity field. And this is the ingredient that, you know, is extremely appealing for this field, because this gradient, so the existence of the velocity gradient gives us the irrotational flow that provides the mapping between fluids and say a black hole physics, or, you know, quantum field theory in curved spacetimes. So this is great, but and Silke already opened this. Any quantum fluid, including superfluid helium, contains quantum vortices, which are topological defects. And in case of superfluid helium, each quantum vortex carries a circulation quantum, so a quantum of a vortex strength. So if you want to make a large draining vortex in superfluid helium, the only way to do it is actually to take many of quantum vortices and stack them into a small vortex core, so that, you know, that the strong vortex flow is actually due to a combined, or, you know, summed effect of many quantum vortices. And here on the right is actually a computer simulation of how these quantum vortices usually arrange themselves in space. So if superfluid helium becomes turbulent, they create this very dense, very complicated mesh. And we would like to avoid this. So we started playing with first some mock-up setups, how we can actually tame the flow of superfluid helium. And we need to overcome basically two challenges. So first one was to find a way how we can circulate helium in a closed bathtub. So how can we set this up in such a way that we can actually enclose everything in a cryostat, so in a vessel. And the second is how to get rid of all these extra vortices that would somehow make our life a bit more difficult when describing the analogy. And so our solution, after about 2 years of playing and the trials and various errors and so on, was actually this kind of approach when we created a closed loop bathtub. So essentially, we are spinning a propeller at the bottom of a container that contains superfluid helium, and this helium is pushed through a bespoke flow conditioner that is somehow taming the flow in such a way that the experimental zone, which is here in the top of our closed loop bathtub, creates a draining vortex flow. So we actually get a very deep surface depression, or even a full, you know, open core tornado that extends into this region here. And yeah, so this is a scheme, but actually we are very happy to show that we can actually see this in real experiment. So here on the right is a picture of superfluid helium, so a picture of a liquid that I think in here is around 2 Kelvin. And the draining vortex, or the quantum tornado, as we like to call it, can be found here. Superfluid helium has a very low refractive index, so it might be a bit hard to see maybe, but here around this parameter is the level of superfluid helium, and you can see here are some reflections. Here are some reflections of light. We were able to take this picture just because we are closing our experiment in a fully transparent cryostat made of glass. So we can, at every instant, we can see absolutely beautifully what is happening in the system, how the vortex evolves in time, and how tiny waves are actually propagating. Already from the picture, you can see that the interface of superfluid helium is actually not so smooth, not so calm. There are some surface waves propagating over it. And now the question is, how can we read out these waves? Because in order to use this as a gravity simulator, the experiment needs to provide quantitative data. So we need to get surface elevation as a function of space and time. And that was the second challenge, how to extract this data. And the idea was actually borrowed from black hole physics. So people who are studying propagation of fields around black holes are using some advanced mathematical tools. And one of the ideas behind this is that actually if you are looking at individual modes, so individual waves with a well-defined frequency and wave number, these waves actually get shifted due to the velocity field created by the vortex in a very specific way. So here this term f of k accounts for the dispersion, so it accounts for the fluid properties of either water or helium. But the main point is that actually this tiny frequency shifts here, if we find a way how to pick up them, we can then actually describe the velocity field, and from the velocity field we can start generating the effective metric that the waves experience. So the realization of this idea, how to actually resolve these frequency shifts in both space and time, is actually in its principle very simple, and I think I can say for both of us that we're really amazed that it worked so beautifully from the very beginning. And the idea is to actually observe the superfluid interface against a pattern. So here, from the top of the experiment, we are observing our vortex generating system with a high-speed digital camera. And here on the right is actually the output of the camera when there are no waves on the interface. And you can actually see that there is this pattern that is actually glued at the bottom of our experimental zone. And the pattern seems nice and regular because there is nothing to distort it. But as soon as we start generating waves, and I hope you can see it on this video, the waves really visibly affect the pattern. So these tiny ripples, they are actually bending the light, and this deformed pattern is our measurable quantity. We can record, and we actually did record very long and very fast movies of this deformed pattern. And there is a technique called synthetic Schlieren imaging that allows us to backtrack these deformations and to reconstruct the topography of the interface that resulted in the deformed pattern that we happen to be observing. So from these movies, through several steps in image and data processing, we are able to reconstruct height fluctuations. And this is just one snapshot in time. So we actually resolved this height everywhere where we see the pattern. So unfortunately, we don't see the central region where the vortex core is, but we have this massive range of space where we can actually observe how surface waves are propagating. And they are propagating in two directions. So they're either propagating from the vortex here in the center towards larger radii, but because this is a closed system and the damping of superfluid helium is extremely low, these waves can actually travel all the way out and they can reach a boundary, right? This doesn't really happen in the outer space. If you have a field propagating from a black hole, it probably traverses very large distances until it gets, for example, reflected. In our case, it's a bit different. So these waves can actually reflect from the solid wall and continue back towards the vortex. And this ability to track the waves, as they propagate back and forth, turned out to be absolutely crucial to discover really intriguing phenomena about rotating black holes. So what we do with this height field, of course, is that we want to transform the height fluctuations into actual modes, because we are still trying to measure these tiny frequency shifts due to the velocity field. And if you look on the height fluctuation field at the moment, it doesn't look very structured, right? There are plenty of waves, there are probably different frequencies, different amplitudes, etc., etc. So we started decomposing this complicated structure into something that is more tangible. And we first started by Fourier transforming the azimuthal coordinate into what we call an azimuthal number. So the azimuthal number m counts what is the periodicity of the wave as it revolves around the vortex. So here you can see some four-fold symmetric waves and 12-fold symmetric waves, etc., etc. But we can go further and we can also transform time to obtain frequency. And from this, on the first sight, very incoherent picture, we actually resolve very structured behavior of surface waves in superfluid helium when looked in this two-dimensional Fourier space. So what you can see here are actually plots for two different radii. And here in the upper plot, for example, you can see that all the excitations, they are living in this quite confined piece of Fourier space, whereas all the other areas are very poor on additional excitations. And then we started thinking, what can be the reason, right? We can actually find the boundary between the excitation-rich and excitation-poor regions. And the physical reason behind this is really fundamental, and it really circles back to the basic idea that the systems should describe a curved spacetime. So if we look on one particular mode, so in one particular point defined by its azimuthal number and its frequency, at different radii, this point can actually sit either inside or outside this cone where the fluctuations are abundant. And the reason the case when this point actually sits outside, it is when we try to solve the wave equation or the dispersion relation for these waves. So we find that in this case, the only solutions in terms of the wave number k are complex. And the waves with complex wave numbers are called evanescent waves. They are exponentially damped. And this exponential damping explains why there are no excitations outside of this cone. And then as we increase the radius, we actually start finding real valued solutions. And these solutions come in pairs. And these pairs are essentially radially ingoing and radially outgoing waves. And this whole landscape can be quite neatly represented with this following scheme. So for very large radii, we have these two solutions, so these two branches, where at the bottom we have radially ingoing and at the top we have radially outgoing waves. And as this wave, that is, say, coming from large radii towards smaller ones, it just follows this solution. And at some point, at this red point here, when it hits the boundary, so when the wave actually tries to leave the cone of excitations, it actually reaches a point where its radial wave vector is 0. And then it can actually scatter into either an evanescent wave that continues further to smaller radii, or it can become a radially outgoing wave. So in the end, this radially ingoing wave, by interacting with the vortex flow, can actually become radially outgoing. And this reminds me very much of this picture, or this small animation that Silke shown. If you have a curved spacetime, you are actually obtaining, same kind of behavior, right? So a radially ingoing wave can become radially outgoing, but in the gravitational, language, it is not caused by the effective effect of the velocity field, but it is caused by the curvature of the spacetime. So the ability of reflecting these waves is actually something that already hints that our system indeed works as a simulator of a curved spacetime. And in more technical terms, we describe this boundary here as some sort of a scattering potential, because it scatters these waves. And in general, the scattering potential depends on the properties of the fluid and the settings of the experiment, but it also depends on the value of the velocity field. And up to this point, we are not sure what is the velocity field. And we need to know the velocity field to show that our quantum vortices, which are supposed to be creating a massive vortex flow, are all compressed in a small vortex core. And the region that we are actually observing is free of vortices, so that we can tell that it is irrotational. And with this very powerful tool, with the way of understanding, this appearance and disappearance of different wave modes, we're actually able to understand our system and to learn 3 valuable lessons so far. So the first one, by finding this boundary between excitations and no excitations, we're able to measure directly the velocity field. And we were measuring it in 2 different scenarios. So in the first one, it is when we are driving the system only very gently. And the interface, so here is the superfluid interface, it only forms this finite depth depression, which is the vortex flow. So here is actually a larger contrast sketch of it, which we call solid core, because the core of the vortex is actually filled with superfluid. And the superfluid, if our assumptions are correct, must contain this very dense tangle of quantum vortices. If we increase the drive, we can actually deepen this depression all the way down to the drain opening of our system, and we can create what we call a hollow core. And this hollow core actually changes the topology of the system. And what happens there, it is that this quantum vortices actually fuse with the hollow core and form a single but multiply quantized quantum vortex. And well, long story short, our velocity measurements are actually very nicely consistent with this picture. They show that indeed the area where the waves are propagating is very nearly irrotational, so it can be accurately described by the whole mechanism of these gravity simulators. And the core of the vortex is very compact and is very strong. Actually, on panel B, it is the number of circulation quanta, or number of quantum vortices that are trapped in the vortex core. And you can see that the prefactor is 10 to the 4. So these are tens of thousands of vortices which are forming our macroscopic velocity field. And these are actually one of the strongest quantum vortex flows ever created in quantum fluids. The second lesson is already relevant to black hole physics, and I'm going to discuss something what is called bound states. So here it's going to be a bit difficult plot to follow, but I'm going to reveal it to you step by step. So first, I'm plotting here an effective potential. So the effective potential that we can retrieve experimentally. And here it is actually plotted as a function of the radius for one particular wave mode. If I plot the spectral amplitude of surface waves that are corresponding to this wave mode, I see this very distinct stripy pattern. And each line of stripes is a different standing wave. So a wave that is trapped from the left by the effective potential, and from the right by the fact that actually, our system is finite size and it contains a wall. And what is really beautiful is that we can actually look into this individual bound state, we can extract their amplitudes, and we see a one-to-one analogy with a quantum particle trapped in a potential barrier. For example, if you look on this example 1 here, you can see that to the right of the potential barrier, the wave is essentially a sinusoid, but to the left of the barrier, the wave is not just simply reflected, but in total analogy with quantum mechanics, it actually becomes exponentially damped as it penetrates the barrier. So unlike classical systems, this simulator can simulate quantum tunneling, or the analog of the quantum tunneling in a wave system. And what we did in the end is that we actually took, again, a mechanism or a mathematics used in black hole research, and we were actually able to create an analog, mathematical description that very accurately predicts these bound states or their frequencies. Then, by increasing the drive, so by changing the system from the solid to the hollow core, the picture remained the same. So, across a broad range of frequencies, and later we found out also across a broad range of temperatures, we were able to actually, describe our system with a relatively simple set of theoretical tools. And the third lesson that we learned, and this is already something that is extremely relevant for current research in black holes, it is the observation of these ring-down oscillations. So Silke already introduced it, but the ring-down is essentially a set of characteristic frequencies that a perturbed rotating black hole radiates from its ergo region all the way towards infinity. And here is actually a cartoon how this ring down can happen in our case. So to the left is a vortex core that can be somehow perturbed, and these perturbations, they are propagating through the potential barrier, and then they are propagating to the experimental zone where we can actually read out these waves, and we can actually check whether the frequencies that are excited in the experimental zone are indeed corresponding to the frequencies that should be predicted for this kind of a system. And one of our PhD students, Leonardo, he actually developed a numerical model where he found that these characteristic frequencies can indeed are predictable. So you can actually find where these frequencies lie. And most importantly, he found that due to the confinement, due to the existence of the finite size of our system, these characteristic frequencies actually shift. And he managed to calculate these shifts, and he was able to provide updated or more accurate predictions of these characteristic frequencies. And to our surprise and excitement, we actually observed very sharp peaks lying exactly where they were expected to see. So in the end, what our experiment can simulate is not just a rotating black hole, but a rotating black hole which is actually undergoing spatial confinement. And this is really exciting because there are theories out there who are predicting how black holes can be surrounded by either plasma or known forms of matter, but also by something more exotic, such as axion halos that can provide a similar spatial confinement. So here on the Earth-bed experiment, we can already probe properties which in the outer space are formed from very exotic objects such as black holes, and not yet known forms of matter such as axions. So to summarize, this is just the start of what I hope will be actually a long and hopefully successful research program, because this experiment is up and running for only about a year and a half, and we still have plenty of helium and plenty of memory on our hard drives to fill it with exciting data and to find new discoveries. And before I really conclude, I would like to actually mention that this is a massive group effort. So our group is called the Gravity Laboratory Group. It is a very diverse and very lively group. We are currently about 15 members, including Silke and Jorma and some other senior members of staff. We are spread across not 2 laboratories, but also in a room called the Art Lab, which is a room or a space where we are trying to merge art with science. We are actually collaborating with a number of artists, and one of them is actually Alistair McClymont, who I believe is now on his train to Nottingham to visit us for the next couple of days. And you know, because you know all these experiments and all these ideas that we are getting, they are relying quite heavily on, you know, out of the box thinking and you know, bringing with new ideas and you know, having a large team of young people who are, you know, very much able to think out of the box is really helpful. And the last mention is that we have an Instagram website. So if you'd like to follow us, feel free to scan the QR code and you can get updated about all the fascinating news that are happening in Nottingham. And so with that, I would like to thank you for your attention.
Wow, thanks a lot. Let's give some clapping hands to Patrik as well.
Thank you.
So now there's time for questions again. Also, if you want to ask something regarding the first talk, just feel free to raise your hand and then we will call you out. I think we have the first question. Somebody from the Gärtner group.
Yes. Can you hear me?
Yeah.
Yeah.
Okay, great. So first of all, thanks for the great talks, duo here. I was just wondering about the imaging kind of setup that you have with this detection scheme. Maybe this is a naive question, but is it like a priori clear that you always can have like a unique reconstruction of the actual like surface pattern based on some kind of distortion of this pattern on the bottom or that you have there, this checkerboard pattern? Is this always clear how to do this, or maybe are there some assumptions needed here?
Well, you need to meet quite straightforward assumptions that, you know, your camera needs to be far away so that you don't get like parallactic distortions and so on. And then of course the method works for small deformations. If the wave is too steep, and for example, if your pattern moves more than by a period, then, you know, it becomes too difficult to reconstruct. And maybe, sorry? Yeah, you can then you can change the spatial frequency of the pattern. If your wave amplitudes are too high, you can use a more coarse pattern, which is less sensitive, but, you know, it has a larger range. And yeah, actually, the pattern that we are currently using, you know, it was an iterative process when we, you know, when we tried to refine it until we were able to.
Okay. Thanks.
If you'd like to comment further, Silke, go ahead.
I mean, you can also, instead of a physical pattern, use interference pattern. Then it works as well. Yeah, it's what Patrik. I mean, what Patrik said is not working everywhere, but it's pretty robust, to be honest. We were also quite surprised how, because the refractive index is very small in helium, so we weren't quite expecting to have such nice results. Retrospectively, it made a lot of sense, but it was a bit of a surprise to us. Also surprised that nobody used it in helium before. Yeah, one of these things where, you know, something that is a great thing to use and has just been missed, to be honest.
Okay, I think this has answered the question. Yes, very good. Thank you. May I also ask some question in the meantime? Actually, I read the paper a couple of times, but now that I saw the lessons learned 2 slide, I wonder about the excitations you saw for the deep core below the curve. So if you could maybe go back to lesson 2. Yes. So in panel B, yes, exactly this, yeah. So how do I do this?
So there are 2 explanations, and you know, without looking more accurately in the data, I'm not sure which one is the correct one. So one is actually, these can be actually waves coming from the vortex core, because you know, the vortex core that we see even in this deep core regime might have some sort of small turbulent layer around it, and this can be actually signatures from it. Or the second, and I think that is maybe more likely in here, it is that, you know, you see, so here I am actually plotting, you know, frequencies from 0 to 40 hertz, but these are waves that are co-rotating with the vortex. So there is a second, you know, second half plane of excitations which correspond to waves counter-rotating to the vortex, and I can plot them as, you know, negative frequency waves. And these negative frequency waves experience a different effective potential than the co-rotating ones. And what happens is actually what Silke said, is this frame dragging, when, you know, counter-rotating waves are interacting with the vortex flow in such a way that they actually become co-rotating. So they can actually leak from the negative frequency half plane to the positive frequency one. And I think this might be actually an indication of that.
I see. And maybe I would also believe, just from scratch now, the second option, also because you see that this also follows this very same effective potential curve you have for the other excitations, right?
Yeah. The effective potential for the counter-rotating is similar. Then it somehow, you know, it reaches a local minimum, but, you know, these are just technicalities.
Yes. Thank you. Is there another question by the Gärtner group?
Yes, if it's okay.
Shoot.
So, hi, thanks for the great talk, both of you. So I was just wondering, so for both experiments, you mentioned the water one and the liquid helium one. If I understand correctly, your black holes are two-dimensional, right? Is that correct?
Yeah.
And my question would be, what implications?
Because when you say it's space-time, so it's two space, one time.
Yeah, 2 + 1. But cosmological black holes are 3 + 1, right? So I was just wondering what the implications are in how far the conclusions you get in 2 + 1 also transfer to 3 + 1 dimensions, and maybe if there is a way to go to 3 + 1 in the lab also.
So there is a way, but you don't gain much more, and I need to explain that. I just need a metric. Sorry. So this is a very good question. So the thing is, this metric here, I had a different one. This is, sorry, I need the one which is this one. Perfect. Sorry, a bit of a lag. So if you look at this metric, so if you look at a 3 + 1 dimensional black hole and you look at a Kerr solution, okay, which is sort of the standard black hole that we consider. It has angular momentum and a mass. If it's Kerr-Newman, it also can have a charge, but we don't observe charged black holes, so it's an angular momentum, spin, and a mass. And then if you look at the solutions that you get, this would be these Kerr solutions. Now, one thing that has been shown as a theorem is that these Kerr solutions cannot be cast onto a space-time geometry that is flat on the spatial slide. What does this mean? So if you look at this block here, this is what we call the spatial slice. And it's conformally flat. It means these are the zeros around except of the diagonal. And it's conformally flat because the whole metric here is a conformal factor that I didn't write down. It's just a proportional. And you can show that Kerr cannot be cast onto this. Okay, so the only way to get something off diagonal is people played with relativistic fluids. That was work by Matt Visser and Stefano Liberati. But just from this, I can already know I can't map a Kerr solution onto this. Now, then you can ask yourself, what is it then what you get? So this is a metric, and the question is, does it exhibit all the interesting features? Okay, do you have an apparent horizon or a black hole horizon? Do you have ergo region? Do you have all this? It possesses all of this. But now you can ask yourself, could I get some features of really Kerr And we've shown with Matt Visser together, we've shown that if you take magnetohydrodynamics, the most complicated fluid flow where you can have external fields manipulating flows, you could mimic the equatorial slice of Kerr. And that's where all the interesting, or most of the interesting features is that we are interested in. But this is already something not natural. So if you take a fluid flow, you get these irrotational velocity flows. These irrotational velocity flows, they have a fall off that is slower than the angular momentum falls off in an actual black hole, and that has a physical consequence, which if you look here, this pattern here, if you count the wave crests around it, you will actually pick up that you get additional wave crests coming out. This is the water wave equivalent of the Aronoff-Bohm effect, and Michael Berry actually predicted that. So, and this is there because the velocity profile, the velocity field falls off slower than around black holes. So they are very different. And I always say that the goal was never to reproduce the black holes out there. The goal was to have systems that where we get the same kind of physics processes to have, to the same physical processes to occur, superradiance, frame dragging, ring down, and maybe back action, some of the things that we're testing, but they are not the same. And you cannot, even if you go to 3D, in this system, you cannot get Kerr. You could get equatorial Kerr if you go to magnetohydrodynamics. That's the best you can do.
Thank you.
So here it is with the wave crest. I can just, if you go and count the wave crests here along this line, when you count the wave crests around the upper line, you see that you have more on the top. They seem to come out of this. And Michael Berry has a nice paper about this. And just from this doesn't happen around black holes. It wouldn't occur.
Mm-hmm. I see. Thanks a lot.
So there is another question by Claudio. Please go ahead.
Hey, sorry, I'm in a common room here, so I try to make it quick. So when you say all these effects, I reckon the waves do not have any helicity, so you wouldn't expect to see some spin Hall effects or so in the perturbations, like some rotation coupling.
Yeah, I want to say I agree with you.
Or maybe asked differently, would there be any chance to try and test some spin Hall effects in this setup?
So I am actually now, I need to remind myself, to be honest, I'm a bit blank now exactly what you need to see it. So I can't really answer the question. One thing I can maybe to partially answer your question, if you look at the kind of field dynamics you get, these are scalar fields. They can be massive, but most of the cases we are working with massless scalar fields. There are extensions to this efforts, but nothing that has been implemented in the lab. So theoretical extensions. And I would need to actually look up exactly what you have in mind and think about it. The answer at the moment is I'm not aware of that anyone is doing this.
Yeah, I reckon you would need the internal degrees of freedom, so you would need have to have some spin degree of freedom in the field. So yeah, I reckon if you just have scalar fields, there should be nothing.
So there is a model by Wen and collaborators, and this goes back a long time ago, where they look at the quantum rotor models, and then they get spin excitations to have can you get gravitational waves? There's nothing conclusive that I know of really. People have been in spin 1, spin 2 particles. They have been trying to get to this. There is some theoretical work on it. Would be super cool, goes without question, if we had that. However, I do not want to say no. I don't want to say no because I have thought no many times before and have been wrong. And then somehow we found ways around it. this, I think, maybe to pose it back, if you could find something like that, that would be really nice.
I mean, we have the spin Hall effect worked out for like arbitrary fields, basically in curved spacetimes. So there should be an analog, but I don't know.
You know, we're throwing this back at you and say, like, this would be something we would like to have a theoretical framework for this. This would be wonderful.
Well, I mean, the question is more whether you can have perturbations that have a internal structure, I reckon. Like if you can have perturbation, like what do you, so this is the experimental question to play the ball back is like, can you have any perturbations on top that have an internal structure, so that have a spin?
Yeah, no, finding, what I mean is the framework to find an experimentally accessible system where you can establish the mapping. So I know that the theory is worked out, but when I talk about the framework, I mean, I'm saying you identify a physical system that can be set up in the lab, and then you identify a parameter regime where you can make the mapping to what you have in mind. So the framework would be to find the translation key, to find the physical system where you could do it. I do not foresee straight away how you could do this in helium.
But there are helical waves in sound, right? Maybe some optical systems.
Yeah, but you still need. I don't want to say something wrong now. I mean, theoretical work people have. Yeah, I can't remember. So maybe someone else in the audience know the answer. Maybe some people. I can't. At the moment, nothing comes to my mind that would directly work.
Mm-hmm.
I don't know what to say, honestly. I also don't have a clear answer at this point. Do we want to leave it like this, or?
Yeah, because
that's science, right? Science leaves, leaves open questions sometimes.
Yeah, sure.
I would expect that there is more work on this somehow, because it is an interesting question and an interesting thing to do. One thing that I can just say where I see sort of the community going is looking at nonlinear effects. First order phase transition is already really hot topic, is part of the network program. And then the other thing is what we recently discovered and also translated to helium was looking at all the nonlinear terms in the wave dynamics. And that was to me a big surprise that you can actually make some mapping to cosmological relevant systems and really use those to run nonlinear processes, which are really hard to simulate, and state-of-the-art simulations are struggling. So that I would find really, really exciting. And so that's something, people, when I started my PhD, people were saying the nonlinear stuff is really what we don't want. There is no analogy, it doesn't hold. And there was this sort of, it was unthinkable what we're doing now. And so with that in mind, I don't want to say ever again no. We also looked at back action, which was saying they cannot learn anything about it. And this is also becoming a big topic. Back action here, how you change the fluid flow as a consequence of Hawking radiation, other things. Many people are looking into this. It's clear one way to look at this that we know now, if you have waves, they can also interact with the zero mode, so zero frequency mode, hence the background. You have interactions with the background as well. So naturally, this is provided in the systems. And sometimes it does make sense to look at it in terms of not that you have the fully nonlinear regime of the fluids, but you really consider individual processes of how, for example, entanglement would spread by interacting with the background and so on. And then you need to ask the question, how can I translate this to real black holes? So, there is a lot of things that we thought that doesn't make sense. we are actually doing right now. And I think that's why that's an interesting field of research that makes it still a field where there's a lot to be done, a lot new things to discover, all the different physical systems. So that I was very surprised by that myself, how far we can push these analogies and how far we can use, how much this concrete simulations can reproduce.
I totally agree. Are there any more questions now? I don't see any hands up. So therefore, I would say we thank both speakers again. Thanks a lot. It was really a pleasure having you. And maybe just one or two announcements for next time. We will meet again in 1 month with Nathan Goldman and Julian Leonard talking about the first realization of a fractional quantum Hall state. This was an experiment done in the group by Markus Greiner. And we can also confirm already the third talk, which will be delivered by Martin Plenio and one of his postdocs on quantum sensing. We are currently watching out for finding somebody more into the high energy physics direction for talk number 4. If you have any suggestions yourself, feel free to just drop an email, because we consider everything we get as input from the community. And with this, I would also like to thank everybody who attended today. If you liked it, spread the word, try to help us grow this seminar. And I think that's a good point to stop for today. So thanks again, Silke and Patrik.
Thank you very much.
Thanks, Torben.
Thank you.
Bye, everyone.
Bye.
Thank you. Bye.
Bye.
Bye.